In problem number 6, we want to fill in the blanks to tell whether or not the original is a function, if it's one-to-one, and will it have an inverse. So if we look at the first function, we know that it passes the vertical line test, so it is a function. If it passes both the vertical and the horizontal line test, it is one-to-one. However, this function does not pass the horizontal line test, so it is not one-to-one. Since the function is not one-to-one and does not pass the horizontal line test, then there is no inverse function. For the next one, we can see that it passes the vertical line test, so it is a function. It also passes the horizontal line test. That's not a very good horizontal line. That one's better. So it is one-to-one, and it will have an inverse function. For the next one, it does not pass the vertical line test, so it's not a function. It's definitely not one-to-one, and we will not have an inverse function. For inverses, they always reflect across the line y equals x. So that is the answer to number 7. In number 8, if we want to sketch the inverse of this function and we know the coordinates that it goes through, all we need to do is flip-flop the coordinates to sketch the graph of the inverse. So if our original coordinate is -2, 3, the coordinate for our inverse is going to be 3, -2. If we have an original coordinate at 0, 1, we're going to have a coordinate at 1, 0. We'll have a coordinate at 0, 2. We'll have a coordinate at -4, 3. And there's not a space for it, but our final coordinate will be at -5, 4. So if we graph that, we'll have a coordinate at 3, -2, 1, 0, 0, 2, and -4, 3, and at -5, 4. So our inverse will look more or less like that function. For writing absolute value functions as piecewise, we first want to know where our function is greater than or equal to 0. So I'm going to first solve that. So I know that x is greater than or equal to -6/5. So my absolute value will equal the original as long as x is greater than or equal to -6/5, and it will equal the opposite when x is strictly less than -6/5. Remember, we only need one equal to sign, and it doesn't matter if you put it on the top or the bottom. We'll skip around a little bit and first cover C before we do B. So we want to start this off the same way. We want to set our function greater than or equal to 0. And then if we look at this one, this is one of the great OR problems. So we want to factor it. And we know that our two answers are going to be -4 and +4. And we want to draw our ORs on there. So we can see that x will be greater than or equal to 4, or x will be less than or equal to -4. So for this piecewise function, we'll have our original, x squared minus 16, as long as x is greater than or equal to 4, or x is less than or equal to -4. And we'll have the opposite, -x squared plus 16, when x is in between 4 and -4. For B, we want to start off the same way by setting our function greater than or equal to 0. Except in this one, when we divide by a negative, we need to remember to switch the sign. So our function is going to equal the original, this time when x is less than or equal to -4, and it will equal the opposite when x is strictly greater than -4. For part D, we have -3x plus 6 over x minus 2. So we want to be able to have the same thing on top as the bottom. So I can take a -3 and factor it out. So I have -3 times x minus 2, absolute value of that, over x minus 2. And then I can actually take my 3 and factor it outside of the absolute value bars, and it becomes a +3. So when we write our piecewise function, since we have x minus 2 over x minus 2, that's essentially going to go to 1. 1 times 3 is 3. And this will happen whenever we plug in a number strictly greater than 2. 2 is the number that would make our function undefined. And then we will get -3 as long as we plug in an x value that is less than 2. In number 10, we want to find the domain of the square root of 1 minus x squared. Well, we know that when we take a square root of any number, it must be positive. So 1 minus x squared must be greater than or equal to 0. But that looks a little bit funny to solve, so I'm going to rewrite it as -x squared plus 1 is greater than or equal to 0. And then I'm going to multiply through by negative so I can factor it, but when I do that, I need to remember to change the sign. So now I have x squared minus 1 is less than or equal to 0. This changes this to a less and problem. So when I factor, I get x plus 1, x minus 1 is less than or equal to 0. And when I draw my number line, I know my answers will be at -1 and +1, and my arrows need to come in. So my domain will be in between -1 and 1. For part B, we want to find the domain and range, and we need to just look at the graph and be able to tell. So we can see that the x values are in between -2 and 2, except the x values come really close to 2, but they don't include it. So the domain for this graph would be -2 with a bracket and then a 2 with a parenthesis. The range for this function, if we scan up and down, we see that our function starts at 0 and it goes up to 3, and it includes 0 because even though there's an open circle here, there's a closed circle here. So our range would be bracket 0 to 3 with another bracket since the range includes 3. For number 11, we want to graph the piecewise function x plus 7 when x is less than 1 and x minus 1 when x is greater than or equal to 1. So first I'm going to make a table for x plus 7. And I'm only going to plug in numbers that are 1 or smaller. I'm allowed to plug in 1, but I must remember that that is going to be an open circle or an open dot. So if I plug in 1, I'm going to get an 8. If I plug in 0, I'm going to get a 7. If I plug in -1, I'm going to get a 6. So we'll start with those values. So if I plug in a 1, I'm going to have an 8. If I plug in a 0, I'm going to have a 7. And if I plug in a -1, I'm going to have a 6. I also want to draw my arrow in the correct direction. So since x is less than 1, I want to draw my arrow this way. And I made a mistake. I forgot to make my first dot an open dot. So I'll erase him and make him open. All right. Now for the next part, I'm going to have x minus 1 and make another table and only plug in numbers that are 1 and bigger. So this time when I plug in 1, this is going to be a closed dot since it could equal 1. So if I plug in 1, I'm going to get a 0. If I plug in 2, I'm going to get a 1. If I plug in 3, I'm going to get a 2. So I have a point at 1, comma 0. It's a closed dot. And I'm going to have a points at 2, comma 1 and at 3, comma 2. My point's a little bit high. And I want to draw my arrow towards the x's that are greater than 1. And that is a piecewise function. Problem number 12 will be an extra credit type of problem on the quiz. So first, if I want to subtract the absolute value of x plus 4 minus the absolute value of 5 minus x, I need to write each one as a piecewise function. So I'm going to write x plus 4 as x plus 4 as long as x is greater than or equal to negative 4, since negative 4 is the key point, and negative x minus 4 as long as x is less than negative 4. Now I'm going to do the same for 5 minus x. Now this one's a little bit more tricky because we'll have 5 minus x as long as x is less than or equal to 5, because the negative x flips the signs, and a negative 5 plus x as long as x is strictly greater than 5. So now I'm going to make my 3 intervals of where this can happen. So my 2 key points are 5 and negative 4. And for our first one, we can have x plus 4 as long as x is greater than negative 4. So I can write an x plus 4 here and an x plus 4 here. And I can have a negative x minus 4 as long as x is less than negative 4. So that would go here. And then for the next one, I have a 5 minus x wherever x is less than or equal to 5. So I'll have a 5 and a negative x. And I'll have a 5 and a negative x. And as long as x is greater than 5, I'll have a negative 5 plus x, or an x minus 5. So now the tricky thing is these values are going to be subtracted from each other. But when we subtract, it's easier to turn it into a plus sign and then just change the signs of our values in the second polynomial. So if I add these together now, the x's will cancel and I'll just have a 9. In this one, the x's won't cancel, so I'll just have a 2x minus 1. And in the next one, the x's will cancel, and I'll have a negative 9. So the answer to this, as a piecewise function, is that it will equal negative 9 as long as x is less than or equal to negative 4. It will equal 2x minus 1 as long as x is in between negative 4 and 5. And it will equal positive 9 as long as x is greater than or equal to 5.